Hello, everyone. Today I will be doing my exam 4 review part 2 on chapter 13, mass spectrometry and infrared spectroscopy. So, a lot of the time I will, and a lot of other people will refer to infrared spectroscopy as IR spectroscopy. It's just a faster way to say it and a faster way to write it. So, infrared spectroscopy, IR spectroscopy, the same thing. Just want to make that clear before we start. But first, we will be talking about mass spectrometry. And generally, mass spectrometry is exactly what it sounds like. It's a way to analyze the mass of a molecule. And the way that this occurs is we use a machine, basically. We put the molecule in that machine, we bombard it with electrons, and it knocks off an electron from the molecular ion, sorry. And where it knocks off that molecular ion electron will tend to either be a lone pair, such as on like an oxygen, or from a bond. And what will happen is we end up with something called a molecular ion radical cation. And then what will happen is that will spontaneously it will spontaneously fall apart into its radical and cation form. And what we are interested in is the cation form, because what we do with those radicals and cations is we essentially put them through a magnet, which sort of spins them and deflects them, which in a way that is proportional to their mass and their charge. And in this way, we can sort of see the masses of the different fragments of the molecule that we get when we bombard it with those electrons. And it'll make more sense once we talk a little bit more about how to actually read this graph. So this is a relatively simple mass spectrum graph. And like we said before, it will be bombarded by electrons, and it will generally knock off other electrons, and then we will have to decide which fragments are those. But first, let's talk about the different peaks that we see here. So this peak right here, this peak that is at 16, this is known as the mass peak. And the mass peak directly reflects the actual mass of our molecular ion. So CH4 has a molecular mass of 16. And so we can see that it falls on the 16 of the x-axis, okay? And then, let me label this. And then we can see that there is a peak right here at m+1. This is called the m+1 peak, and all it is the total mass of the molecular ion plus 1. And that will be plotted on this x-axis here. Okay, this x-axis is the mz. Basically, it's telling us our mass. Okay, and the m+1 peak arises from the idea of isotopes, because different isotopes, such as carbon-12 and carbon-13, exist in the world. And so sometimes you'll get a CH4, well, most of the time, you'll get a CH4 using the carbon-12, but sometimes you'll get a CH4 using the carbon-13. And as a result, its mass will be 1 greater than the regular mass, the M mass, okay? And that's where this M+1 peak comes from. So those are the important peaks on this mass spectrum. But you can see we have multiple other peaks right here, here, and here. These peaks sort of occur because, remember, we are bombarding the molecule with a bunch of electrons. We don't know where those electrons are attaching, and we don't know where the cation is going to fall off along with the electron. So we end up with these fragments, because sometimes, you can see here in this example, the carbon-hydrogen bond will break, and we'll end up with a fragment that has a mass of 15, which corresponds with this guy right here. And we can see again plotted on the x-axis. I'll talk about the y-axis in a second. I just want to talk about the different masses and all of that in relation to this x-axis here. And so we can see here that the more hydrogens that we end up knocking off, so if we have CH2, then we'll have a mass of 14, which is right here. And then if we have CH, a mass of 13, and C, a mass of 12, which we can all see in these different fragments here. Now, longer and more complicated molecules will have more and more complicated fragments. And some of these fragments are more abundant than others. And that is what this y-axis is sort of describing here. It's telling us what is the most abundant fragment for this particular molecule. In this case, the most abundant fragment was the mass peak, okay? And we call this most abundant fragment, the tallest peak in relation to the y-axis, the base peak, which we'll see a little bit further here. We'll see here. So we see with hexane, the base peak, again, the peak that has the largest abundance, is not the same as our mass peak, which is this one right here, okay? And so what we can do is we can say, okay, so what is our most abundant fragment? Like what carbons, what hydrogens make up that fragment? And so what I like to do is I like to sort of look at this chain, and that chain looks like 1, 2, 3, 4, 5, 6. It looks like this, right? And so we can break this chain at any one of these bonds. And so now what I'm going to do is I'm going to sort of, quote unquote, break the chain at each one of these bonds and add them up until I get the actual mass of 57. So if we start from one end, we can see we start, hold on, let me change to a highlighter. We start with CH3 right here. That has a mass of 15, okay? So that's obviously not 57. So I'm going to add again what comes next. CH2, which is 14. That's 29. Not 57 yet. So then I add the next CH2, 15, or not 15, but 14. That adds up to be 43, not quite 57, and then we add this last CH2, and we end up with 57. So our fragment that creates this most abundant peak is this one right here. So what's telling me is that here, this cation is going to be the cation that is most abundant when we bombard this hexane with all of those electrons and then measure the abundance of them, okay? So that is the base peak. And in this case, this group here makes up that base peak. And we can see here that again, here is our M peak, the molecular ion peak, 86 is the same as the molecular weight over here, 86. And then we can see the M plus 1 peak, again, one more mass than the M peak. Obviously, M plus 1 indicates that it's mass plus 1. All right? And so now let's talk about a little bit, how do we tell between different graphs? And somebody asks, in the previous graph, was 16 the mass or the base peak? That's a good question. For CH4, the base peak and the mass peak are the same thing. That's sort of why I didn't mention it here, because it's important to note that the mass peak and the base peak are not the same thing. But sometimes a particular mass spectrum will coincide in order to have the mass peak and the base peak to be the same thing. And the reason why I didn't mention it in this mass spectrum of methane is because then it could get a little bit confusing, because then people would think, oh, the mass peak is the same as the base peak, where that isn't necessarily true. Okay? All right. So let's move on to how do we tell between these different graphs which one corresponds to which structure. So let's, I just switched tabs. Let's go back here. So let's pretend for a second that we don't actually know these molecular weights. Let's pretend that we have no idea what these are. We can't add, somebody asked, if we are not given the molecule, how will we determine what the mass peak is? We'll get into that in a little bit. But generally, the mass peak for a carbohydrate with no extra stuff in it, the mass peak will be the second highest value peak on the x-axis. So in this case, here we can see here is our second highest peak, here is our actual highest peak. The second highest peak is going to be our mass peak. But that is not always the case, such as when we have a chlorine in our molecule, and I'll get to that in a little bit. But generally, if we only have carbons and hydrogens, our mass peak will be the second largest peak in terms of the x-axis, okay? All right, so now let's talk about how do we determine which one of these graphs is going to go with a particular compound. And let's say, for example, we don't know how to do math. We can't add. We don't know how to do that. But we do know that the more saturated a compound is, the heavier it is. Because if you think about it, you can see here C5H12, C5H10, C5H8. All of these have the same number of carbons, but they have different number of hydrogens. And somebody said the second highest peak is the M peak. In terms of the mass, or in terms of the x-axis. So when I say the second highest peak, I'm saying the second highest peak when I'm looking at these numbers on the x-axis. The y-axis is a little bit different, and the M peak is not going to correspond with that y-axis there. Okay? All right. So back to talking about this. So we see here that each one of these have the same number of carbons. So that's not going to change our mass. But you can see here that the more saturated we are, the more hydrogens we have. So as a result, the heavier we are. So if we look at these different graphs here, we're going to say, okay, the one that has the highest value mass peak is going to be our alkane, our pentane. And in this case, that would be this one here. So graph 3 corresponds with pentane. And we can see here, okay, so the next heaviest one, ooh, I dropped it in there. The next heaviest one should correspond with pentene because that is less saturated than pentane, but it's more saturated than pentyne. So that would be this one here. And then finally, that leaves this one to be pentyne. So that's how you sort of tell apart between more saturated and less saturated in terms of triple, double, single bonds, alkanes, alkenes, alkynes. Alkanes tend to be heavier because they are more saturated, they have more hydrogens. Alkynes tend to be the lightest because they have the least number of hydrogens. All right. So now let's get into, so this example here, this has to do with a lot of math. You probably saw it in class. I'm not a fan of doing it this way because most of the time you will be given the actual graph, if that makes sense. So instead of saying the mass peak is 72 with a relative height of 38.3% of the base peak, it'll be shown sort of like this. So like 38 would, I guess, look like this, and the m plus 1 would be 1.7. So usually you would actually see this, okay? And then that way you would be able to tell what the base peak is. And I'm honestly not a big fan of doing this math stuff here. If you like it, then definitely follow that. But this is the way that Dr. Daddy does it. I do it a slightly different way, so I'm just going to go ahead and sort of skip over this slide. Okay, so now we're getting into how do we tell that different compounds have specific stuff in them. So like specifically, how do we know we have chlorine? Well, we can see here that when we have chlorine, we generally are going to have two isotopes of chlorine. Chlorine 35, so chlorine 35, and chlorine 37. The relative abundances, so the relative abundance, which is this y-axis right here. So the relative height on the y-axis is going to relate to the relative abundances of these two different isotopes. So okay, so how do I say this? So the chlorine isotope is generally present in a 3-to-1 ratio. So for every one chlorine 37, there are 3 chlorine 35s. And this is also reflected in the mass spectrum. So if you look over here in the M plus 2 peak, remember, chlorine 37 is 2 more mass than chlorine 35. So we're going to be at M plus 2 rather than M plus 1. So if we look here, the M plus 2 has a relative height of 1 to 3. So it's about 1/3 the height of that M peak. So what that's telling me is that when we have 1/3 the height of an M plus 2 peak for a mass spectrum, that's telling me that we have chlorine somewhere in the molecule. Okay? And this is due to the different isotopes of chlorine and the relative abundances of those two different isotopes of chlorine. Okay. And so similarly, we're going to have two isotopes for bromine, which are already nicely written out for me here. Bromine 79 and bromine 81. Now both of these are about equal when we look at the relative abundances of them. So again, we're going to look at the M+2 peak because bromine 81 is 2 more than bromine 79. And we're going to see, oh, if it's about the same size, so if they have about the same abundances, so it's going to be pretty obvious because while this isn't exactly the same height, it's not as short of something over here, but it's going to be pretty obvious if they're about the same height. But if they are about the same height, then we're going to have bromine. And this is reflected in the first question here of this 13.1 MS Spectroscopy IR Spectroscopy worksheet. So somebody said, so we decide if it's chlorine and bromine simply by the look. Well, it comes into handy here, where A, B, and C, they all have masses total to 122. So we can't exactly tell the difference between these three graphs just by looking at the mass peak. Okay? And so we can look at these, and instead of trying to figure out what these different fragments are over here and over here, what we can do is we can look at the M and the M+2 peaks, okay? So we can see here in graph number 1, we have an M+2 peak that's about a third of the size of the M peak. As a result, we can say, oh, this guy here probably has chlorine. When we look over at our possible choices here, we only have one that has a chlorine in it, so this graph 1 probably corresponds with B. And then I'm going to skip graph 2 and go to graph 3 here. We can see that the M and the M+2 peak are relatively the same size, so we can say, oh, this probably has bromine in it. We can see the only one of our choices that has bromine in it is A, and thus that narrows down to be C. Okay, and I'm sure if you analyzed each one of these by the actual base peak versus the mass peak, then you could probably tell which one is which. But this is a much faster way to do it and a much easier way to do it, in my opinion. Okay, does that answer your question about deciding if it's chlorine or bromine simply by the look, that sort of thing? And so the next thing that we're going to see, it's not on a PowerPoint slide here, but essentially 90% of the time, or most of the time, I'm not going to say 90, but most of the time, you're going to get a mass of an even number. So you saw 122 in that last example. CH4 has a mass of 16, et cetera, et cetera. However, if our mass is an odd number, then that means we have an odd number of nitrogens. And this has to do with the amount of bonds that nitrogen can have. So if we think back, we know that carbon can have 4 bonds, oxygen can have 2 bonds. Nitrogen, on the other hand, can have 3 bonds. Now, this odd number of bonds is going to directly result in an odd mass number. And then when we talk about, you may be asking, well, what about the halogens? They can only have 1 bond. Well, while that is true, since they only can have 1 bond, they sort of act like hydrogens. So they don't really add to or take away from that even number of the mass. Whereas nitrogen, having 3 different bonds, that can result in having an odd mass number. So an example of this would be, let's say CH4 or CH3 CH2 versus CH3 NH, or CH3 CH3 NH, CH3 NH2. Sorry, sort of lost my train of thought there. But if we go ahead and add these together, we're going to have 15 plus 15, that's 30. Our mass number is even. However, if we look over here at CH3 and NH2, that'll be 15 plus 16, because nitrogen has a mass of 14 plus 2 hydrogen. We can see here we end up with a mass of 31. So we can see here directly that if we have a nitrogen instead of a carbon, or instead of an oxygen instead of whatever, we are going to end up with an odd number, okay? So far, the way that we tell if a certain atom is present just by using a mass spectrum is 1, we look at the M+2 peak. If it's 1/3 the size, or 1/3, not 1/2, of the M peak, then we have chlorine. 2, we look at the M+2 peak. If it's the same size, so 1-to-1 ratio, as the M peak, then we have bromine. If we look at the mass and it's an odd number, Then we have nitrogen, or an odd number of nitrogens. If we have an even number of nitrogens, it'll cancel out and make an even mass number. Okay? So the next tell we're going to look at has to do with that fragmentation that I was talking about earlier, which makes those different peaks that we saw. So we can see here that when we fragment an alkane, we're simply going to break apart the carbon-carbon bonds, which makes sense because the carbon-hydrogen bonds tend to be pretty strong. We don't see those fragments very much unless we're looking at something like CH4, which only has carbon-hydrogen bonds. So we can look here at this top one. If we have mass minus 15, so that would be like our total mass minus 15, then we lost a CH3 fragment, okay? And we end up, in this case, with something that has a mass of 57. Whereas if we lose CH3 and CH2, we lose a total of 29 and so on. You don't have to have these numbers memorized, just know how to find them. So like for example, I'm going to make up a number. It probably doesn't actually correspond with any true alkane or anything. But let's say that we have a mass of 80. And I tell you, oh, we see a prominent peak at about 65. What fragment is this? And then you're going to say, okay, what is 80 minus 65? And then you're going to tell me, oh, that's 15. So we probably lost a CH3. So whatever the alkane is, minus a CH3 will be the fragment that makes the peak at 65. So like if I had this is definitely not going to correspond with 80, but if I had something like this and I told you we lost 15 according to the mass, we're going to lose either this CH3 or this CH3. It doesn't really matter. You would then draw the cation that looks like this. Because remember, the mass spectrum is reading the cations and not the radicals. So we're going to specifically draw the fragment being a cation. Okay? All right. So why did we talk about fragmenting like this? Well, different types of functional groups will have different types of fragments. And one important one is mass minus 18, which is the loss of a water, because H2O uh, has a mass of 18, obviously. So if we have an alcohol, then we are going to end up losing 18 for reasons why I'll discuss in a moment. Somebody asked, is CH3 having a 15 mass? Well, let's think about it. C is a mass of 12. 3 hydrogens have a mass of 3. 12 plus 3 is 15. So yes, CH3 has a mass of 15. All right? So let's talk a little bit about how an alcohol loses a mass of 18. So if we look here, scrolling down past that, we can see here that if we end up losing an alcohol, we can sort of stabilize it by having an alkene-ish right here. So what happens is we lose an OH group, we lose a hydrogen group, and then we can semi-stabilize that by replacing that with a double bond, okay? And then we lost this 18 right here, okay? So for example, let's take the 80 example that we had before. If I had said 80, we went to 65, that's a loss of a CH3 group. If I said 80 went to 62, on the other hand, that would be a loss of H2O, telling me that whatever had the mass of 80 is some sort of alcohol. It has an OH group somewhere, okay? So a question like this would be, if I have a mass of this, so a mass of 72, and then I see a prominent peak at 54, what type of functional group is present here? Well, all I would do, 72 minus 54, that should be 18 if I did my math in my head correctly. And so then you'd say, oh, since we lost 18, that means we have an alcohol group somewhere. So our 72 mass is some sort of alcohol. All right? All right. So that's our fourth sort of tell for, oh, here's an example of the alcohol. So we see here our mass peak is at 102, and then we see what's 102 minus 18? That would be, hold on, I'm doing this in my head really quickly. 84? I think it would be 84. something like that. But then we see here, oh, look, here's our peak at 84. That peak of 84 results from the loss of this OH and then one of these hydrogens right here, right here. So that tells me we have an alcohol. All right? Okay. So now we know 4 things. 1, if our M plus 2 spike is 1/3 the size of our M spike, that means we have a chlorine. If our M plus 2 spike is exactly the same size as our M spike, that means we have a bromine. If we have an odd mass, that means we have an odd number of nitrogens. And finally, if we have an M minus 18 peak, that means we have an alcohol. All right? It's a lot to remember, I know, but it makes a little bit more sense when you see them all listed out like this, I'm sure. All right. And so now let's talk about carbonyls. Carbonyls is just the sort of blanket term for anything that has a carbon double bonded to an oxygen. So a ketone is a carbonyl, an aldehyde is a carbonyl, and so on, so on. And so when we have a carbonyl, we're going to undergo something called alpha cleavage. And so what occurs there is when we look at a carbonyl, we sort of consider the carbon that is directly attached to the oxygen as a sort of a starting point. And then any carbon that's directly attached to that carbon is known as an alpha carbon. Okay? And so what occurs here is we can have cleavage at either alpha carbon. So we either have a break right here or a break right here. A break at the blue alpha carbon would make this CH3 group. I'm not sure why it's in the red instead of the blue here, but a break right there from that bond would make us have a CH3, would make us lose a CH3, so we would have an M minus 15 peak. If we broke at the red alpha carbon, the red bond here, then we would have a loss of a 3 carbon group, which would be mass minus, I think, 43, if I'm remembering correctly. So both of these peaks are telling us, so mass minus 43, mass minus 15, that is telling us what types of alpha carbons do we have in essence for our carbonyl. So let's say, for example, I know I have some sort of carbonyl. I know I have a carbon double bonded to an oxygen. And I know that I see a peak at M minus 57 and a peak at M minus 1. Okay? So I'm not going to make you calculate this off the top of your head, but 57 corresponds with a 4 carbon chain. 1 corresponds with a hydrogen. So then what we would do like this. 1, 2, 3, 4, 1, 2, 3, 4 right there. And then we would add a hydrogen to the other side. And then this would be our carbonyl. In this case, an aldehyde. Okay? All right. So let's continue on. Okay, and so the last couple slides of this this section of this chapter sort of have to do with some machinery. So it's not super important to remember until you actually go into the lab, but the higher resolution mass spectrometer you have, the closer you get to the true mass. So all these different masses for carbon, hydrogen, oxygen, nitrogen, they aren't really just 12 or 1 or 16 or 14. They have these 0.000783 or whatever. And so then we can end up having a roughly same mass that is exactly the same. So in this case, a mass of 60. But we can see here that if we have a really high resolution mass spectrometer, we would be able to tell the difference between these 3 because that high resolution mass spectrometer will go out to those decimal points and let us know what our exact mass is, and then we can pair it with whatever we have. Okay? So and then low resolution mass spectrometers will round to 60. And so we can see here why a higher resolution mass spectrometer might be preferred. And then the last part of this section of this chapter is going to be gas chromatography mass spectrometry. Basically, what we do with gas chromatography is we sort of load a sample. This is a very, very simple definition, but essentially what we do is we load the sample into this column here, and we break it up. and the smaller fragments will travel through the oven quicker than the larger fragments. So in this sense, we can split up a sample of multiple molecules into different mass spectroscopies, because the smaller molecules will travel faster than the larger molecules. All right. And so now we're getting into infrared spectroscopy, IR spectroscopy. All right. And so we can see here that infrared light is slightly to the right of visible light, all that stuff. This is just sort of the concept behind infrared radiation or infrared spectroscopy. But essentially what we do with infrared spectroscopy is okay, so we're going to get into NMR later, but right now we're focusing on infrared spectroscopy. So what we do with infrared spectroscopy, ignore all of these math right now. What we do is we bombard these bonds. We bombard carbon-hydrogen bonds, carbon-oxygen bonds, all of these bonds with infrared energy. And this way, that will cause the bond to sort of wiggle. It'll either stretch or bend. And those stretches and those bends can be measured on a graph. Now, the graph looks really messy, really scary, but essentially, let's scroll down here. When we look at this graph, we should be able to tell what functional groups are in a certain molecule, because certain functional groups will have the same sort of signals because they have the same bonds, so they're going to have the same stretch and the same bend. Now I'm going to make this sort of graph a little bit easier for you to read by looking over here. Oh, look, here's the fingerprint region. We're going to ignore that. The fingerprint region isn't super helpful to us because, as the name implies, the fingerprint region is different for every single molecule. So unless you have a reference infrared spectrum, like right on hand, it's not super helpful in determining what functional groups we have. Instead, we'll look at this functional group region over here, which is much more important for us, because this functional group region is where we'll be able to read signals in order to tell us which functional groups are present. So let's scroll down very quickly. So we can see here in this example, we can see that they have relatively similar functional group regions right here, right here, and right here. So they both have this CO and the CH bond signals, whereas the fingerprint regions are very different. So here we can see very clearly that we can see what functional groups we have present, C double bond O, C double bond O, but we can't know what molecule this is for sure through the fingerprint region. Okay? So that's why we are going to use the functional group region to sort of tell what type of molecule we have. Like if we have an alcohol, if we have a ketone, if we have any of that stuff. Okay? All right. And so, like I said before, specific bonds will have specific absorptions. And let's talk a little bit about what causes that absorption. So for a second, I want you to imagine for me that you're this carbon right here. And you're just standing there really happy with a lopsided smile or whatever, and you're holding on to this hydrogen, and I want you to think of that hydrogen as a weight. And that hydrogen weight is 1 pound. So you're okay with swinging that 1 pound around everywhere because it's easy for you. You can swing that 1 pound, you can pump it up and down without worrying that you're going to drop it or throw it anywhere. However, if we increase this 1 pound to 2 pounds, it's going to become a little bit harder for you to swing around. And so you can see that is reflected in these numbers here. So the lighter the atom attached to that carbon, the higher the wave number will be. Okay? And so we can see here, like with oxygen, it has a lower wave number than hydrogen, because we can imagine oxygen as being a 16-pound weight, and suddenly you're not as happy swinging around that 16-pound weight anymore, and you kind of want to keep it still. So that's why that wave number is going to be less than the wave number for hydrogen, because hydrogen is lighter, it's much easier to swing around. Okay? And then in a similar sense, we can see that we have a triple bond, a double bond, and a single bond. So the way that we can imagine this is we can imagine these have differing amounts of like oil on them. So this guy here, you have the strongest grip on it. you can hold on to it really, really well. But with these other ones, they're covered in like oil and stuff, so you have a less strong grip on them. So if you have a really strong grip on your molecular nitrogen, you're going to be more allowed to swing that around more frequently, which is why this higher wave number is here. Whereas with weaker grips, these things are covered in oil, they're going to more likely slip out of your hand. So you're going to want to decrease that wave number as that bond strength decreases, okay? And so that's where all these wave numbers come from. And it can kind of help you understand how each of these wave numbers sort of correspond with each one of the specific functional groups, which we'll see in a little bit with the table that will come up in a second. Okay? So that's the wave number. And here we can see, here is the general area for all these different wave numbers. Okay? So now let's talk about IR signal intensity. The intensity is basically how far down the signal goes. And the stronger signals are going to be associated with more polar bonds. So we can see here in a C double bond O bond, it's very polar, it's going to stretch very far down. Whereas in a C double bond C bond, there's almost no poles because they're exactly the same. So the intensity is going to be much less when compared with that C double bond O. And we can see here with the OH, the NH, and the CH, the same concept is here. The OH is going to have the most intense signal, followed by the NH, followed by the CH. Okay? All right. So now we're looking at IR signal shape. Now, this is probably less important than the other two that we've talked about, because generally the only really broad signal that we'll be talking about is OH. So remember that. The broadest signal that we'll generally be talking about is OH. And this has to sort of do with hydrogen bonding. Let me see if he wrote that on this one here. No, he didn't. So it's sort of about hydrogen bonding. So if we have this OH here, and it has these differing amounts of hydrogen bonding. So it could have two rounds of hydrogen bonding, or it can have no rounds of hydrogen bonding. We can see here that the amount of wave number is going to increase with increasing hydrogen bonding. But again, you don't need to worry about this too much because the only really broad signal we talk about is OH, all right? So now let's look over here and look at these IR absorptions. This table is really scary, but let's sort of suss it out really quickly. So we can see here that OH, we can see 36 to 3200 and it's strong and broad. This is the only one that's strong and broad. So we can see here that's the only one that's going to look like this, okay? NH, and again, the polarity, it's going to hold on very well to that hydrogen because both polarity and the hydrogen is very light, so it's going to be a pretty high wave number. Followed by NH, again, polar has a medium signal, about 3500, 3200, because it can hold on to that nitrogen really well and swing it around really well. And yes, unfortunately, you should probably memorize this table. And now we're going to get into the CH bonds. Now, the CH bonds are a little bit tricky, but you can kind of think of it back in chapter 3. I think we talked about it. If a chlorine has 4 bonds, aka sp3, yeah, it's going to have the least grip on this hydrogen, followed by a carbon that is sp2, and then sp has the hardest grip on that hydrogen. So a carbon sp hydrogen bond is going to have the highest wave number because that triple bonded carbon has a much better grip on that hydrogen than an sp2, which is better than an sp3. And so we can see here that's why generally the wave number will go up as the hybridization goes down. All right? And so on. So we can see C triple bond C and C triple bond N. They're going to be about the same because they're going to have the same rough polarities. They're going to have the same rough strength. And so we can see that. And then how do we tell if something has a nitrogen or if it's a carbon? Well, if we have the mass and we see we have an odd number, then we know we have a nitrogen. And by combining the mass and the IR spec in that way, we can tell, oh, this is what we have in our graph here. All right? And then we can see C double bond O. Around 1700, it's going to be a strong signal because it's polar. C double bond C, 1650, medium signal because it's not very polar. And then this is an aromatic ring. This is probably one of the less important ones, less important functional groups for you right now, because you talk more about aromatic rings in Orgo 2. All right. So that's sort of the idea behind this table. What I recommend to sort of quote unquote memorize this is, I'm sure there's like a billion Quizlets out there with these numbers, but don't just look at these numbers, find graphs that correspond with each one of these functional groups. So find a graph that corresponds with OH and sort of memorize what that tends to look like, NH, CH, all of that stuff. Okay, so now let's talk about symmetry and absorption. Remember when we talk about IR absorption, we talk about the bending and the stretching of bonds. If the bending and the stretching of the bonds are exactly the same in both directions, they will cancel out and we won't be able to read it on an IR spec. So generally, if we have a symmetrical carbon compound, we will not be able to see any IR absorption. We won't be able to tell what functional groups are there. Okay, so now we can see here IR absorption in alkanes. Obviously, we're going to block out this fingerprint region here. Goodbye, fingerprint region. And now we're only going to look at the functional group sort of peaks. See here, we have one single peak here. We can go down and we're going to say, okay, so it's about at 3,000. Usually that and over to about 2,800, 2,900, that's going to be CSP3. So to sort of determine the difference between CSP3, CSP2, CSP, I tend to draw a line at 3,000. Anything above 3,000 will be SP2, CSP2. And then I draw a line at about 32, 3250, 3200, all that stuff. Anything beyond that will be about carbon SP bonds, triple bonds. All right? Okay. So we can see that's an alkane, and then here's an alkene. Here we can see, oh, it's about 3150, that type of stuff. That means we have a carbon double bond, which is also bonded to a hydrogen. All right, same thing with the triple bond right here. Okay, so it's about 3,300. That's where carbon triple bonds to hydrogens tend to stay, that sort of thing. Okay. So, oops, go back. So this is talking about the hybridization effect, but we already discussed that a little bit, and we discussed how to tell the difference between them. So I think we're good on this slide here, both of these slides. Okay, now let's talk about absorption in alcohols. Remember, we said OH will be the only strong and broad signal that we see. So if we ever see something like this, know that it's going to be an alcohol. Or it could also be a carboxylic acid, but carboxylic acids look slightly different. All right? Okay. So finally, we can see here a direct comparison between OH and the carboxylic acid. So an alcohol, carboxylic acid. The carboxylic acid will sort of bleed into those carbon bonds, whereas the free oxygen, the free OH, the alcohol will not bleed into those carbon hydrogen bonds. Okay. And this is sort of because of the resonance effect. You don't really need to know that, but it's sort of because the resonance effect and due to this hydrogen bonding. Okay. And then ketones. Ketones, aldehydes, they're both going to have this C double bond O signal at about 1,700. You can see that here. And so you can see here a lot of this IR stuff is sort of comparing, contrasting with the table, with what you know, with other examples. So let's go over here to this example right here. So match each structure with its IR spectrum. I'm going to go ahead and scroll back up to that table very quickly so we can have that on hand. Sorry if you can hear my dog. He's barking. So we can see right here. So here's our important IR absorptions. So we're going to go in between that and then this problem right here to figure out how to solve these problems. Immediately, I notice in this guy here and this guy here, we have a strong and broad signal. So for both of these, we are going to have an OH somewhere. OH, OH. But then we can see here in this spectrum, we can see that it bleeds into the carbon-hydrogen bonds here. So we know that this spectrum 5 will be a carboxylic acid. When we look over here at our possible structures, we can see, oh, we only have one carboxylic acid, so this one's going to be matched with A. So now we go over here, we see, okay, we have an OH bond here, but no carboxylic acid. We look at our possible structures, we say, oh, here's the one with the OH group, that's going to be F, okay? And you're going to do these with all of them. We see here we have an absorption at 1700. We'll go back to our table. My drawings are in the way, but we see that at 1700 is going to be about our C double bond O. So if we go back, we're going to say, okay, so this guy here has a C double bond O. We're going to look at our structures here, and we say, okay, E is the only one with a C double bond O, so that one's going to be right here. All right? And then finally, we're going to look at this last spectrum here. We're going to see, okay, we have a peak right here. That means we have sp2 carbons. All right? And then we also have a slight peak right here at about 1500, 1600 area. Okay? If we look back and we look at our table, we can see that at the 1600 area, we're going to have a phenyl ring, one of these rings right here. So this one corresponds with C. All right? So somebody said, would you have to determine between two different alcohols for a graph if F wasn't the only one? Yes, but usually there'll be other functional groups present. So like, let's say, for example, along with F, there was an alcohol that looked like this, and it had a double bond oxygen right here. By using the double bond oxygen, we would be able to tell which graph is which. So usually there'll be other functional groups where you'll be able to tell which one is going to be which. All right? So why wouldn't the first graph be A? You mean B? Okay, so yes, this one could be B, but if we look here, we have a spike here at about 1600 and another one at about 1500. That tells me, if I go back to my table, we can see here that when we have this phenyl ring, it's going to be about 1600 and 1500. While yes, this could possibly be B because we have this signal right here, which tells us we have a phenyl group right here, or we have a aromatic ring. That's telling me that this graph is probably going to be C. Okay? It said in the book it said this one was B. Then what was probably up with this question is somebody added in C, which sort of mucked up this question here. And how did graph A have sp2 if it was below 3000? Again, sp3 is going to be above 3000, so that's sp3. Something that's about 3150 is going to be sp2, and then 3300, so like right here, is going to be sp. All right. And if the book said it was B, again, probably what happened is I would say that this graph here isn't totally clear with its numbers and everything. I would personally say it's C, but yes, it could possibly be B. I assume the questions on the test are going to be much more clear than B versus C in this case. Okay? Does that make sense? So while yes, this could be B, I'm more inclined to say it's C because of these signals right here. But honestly, it could be either one. All right? So now, did we look at the peak at 3000 or 1600? To tell if it has an aromatic ring, we'd look at the peak at 1600. And 1 second.